Yes. I would now like to introduce our speaker. Thomas Smits is a historian by training and currently working as a postdoc fellow on the cross-disciplinary Goa project Implicit Bias at the University of Antwerp. Thomas has a PhD from Radboud University Nijmegen, where he worked on a research project which resulted in a prize-winning book entitled The European Illustrated Press and the Emergence of a Transnational Visual Culture of the News, 1842 to 1870, published by Routledge. He is interested in the intersection of history, visual culture, and computational methods, which has led to the development and experimentation with a number of computational tools in understanding the past. And it's this aspect of his work that he will share with us today in his talk entitled The Visual Digital Turn, Computer Vision and the Humanities. And this is such a fitting start to our series. Thus, without further ado, Thomas, the floor is yours.
Thank you very much. So welcome to all, or hello from me. So I will share my screen, but I still have to figure out how that works. Yeah. Oh, no. Wait a moment. This is probably still not good, right? You can still, all right. So we practice this, but it always goes wrong in the end. So sorry for that. There we go again. Right, this should do the trick.
Yes.
Right? Perfect. Okay. So again, thank you very much, and also for the invitation to the organizers for having me here today. So as you can see, I already slightly changed the title of my talk. So I want to talk about beyond text, so visual and multimodal digital humanities. So I've been recently working much on multimodal machine learning and digital visual collections. So that will be at the end of my talk also, because it's currently at the top of my head and research. So I hope to take you along a little bit on the journey. So as Julia already mentioned, I'm a historian of 19th century visual media, mostly, also a little bit early 20th century. And I always have been interested in how we can use computational techniques to study the wealth of images that we have in modernity. So normally my work is, of course, as a postdoc, very much focused on research. I try to apply computational techniques not to make any far-reaching claims, as is sometimes done in the digital humanities, but rather sort of test hypotheses that come directly from fields that I'm interested in, mostly visual history, but also visual culture studies. Distant reading and distant viewing, in my opinion, should always sort of interact with each other. And this is just a sort of caveat to explain how I look at sort of the application of computational techniques. So in this talk, I want to sort of talk about how researchers, but also digital heritage collections can use computer vision and multimodal machine learning to sort of unlock the visual side of the digital and digitized archive. And similar to my own research, I also hope that GLAM institutions like archives try to apply AI and machine learning in a modest way. I sometimes see far-reaching claims there as well. But I think there's also lots of opportunities and lots of exciting things going on. But I think we should also be, we can be a little bit modest. So that's all the caveats gone. Finally, the work that I will be showing in my presentation involves a lot of collaboration with colleagues, especially with my colleague Melvin Wevers at the University of Antwerp, Amsterdam, but also with my new colleagues at the University of Antwerp, and with my former research assistant, Ruben Ros, who is now at the University of Luxembourg. So that's all the introduction out of the way. So today I want to first talk about how DH until now, so digital humanities until now, has been very text focused. Then I want to sort of share with you how the shape of digitized collections and digital collection sort of don't warrant this focus on text. And then I want to show how we can use, first, how we can use computer vision to study the wealth of images in digitized archives. And then now also multimodal machine learning techniques, how we can study the wealth of image text combinations in them. Right. So why is digital humanities text focused? I think this is mainly the result of three things. First of all, most importantly, the availability of digitized sources, right? So as many of you know, from the early 1990s onwards, canonical texts, mostly from literature, were transcribed, most famously, I think, in Project Gutenberg. And from the 2010 onwards, we had this revolution of OCR, so optical character recognition, and HDR nowadays, so handwritten text recognition, that are able to automatically describe digitized historical sources and text. So second, I think the availability of NLP, or natural language techniques, was very important, especially the introduction of LDA, or topic modeling, one of the most frequently used techniques to sort of study digital text corpora on a large scale. And finally, these two things led, I think, to new digital humanities methods. Most famously, I think, Franco Moretti's distant reading concept, right, which he introduced to the 2000s. And all of this led, I guess, as Bob Nicholson called it, to a practical revolution. And I very much agree with this claim, right? So instead of a top-down approach, which researchers used to have to take, right? So they had to go into the archive from the top, start with all sorts of keywords maybe, and then finally come to the sources. These new sort of this practical revolution result in the fact that researchers now have bottom-up access, so directly to the word or token level of the digitized collection. Right. Of course, and especially as a historian of visual culture, you might imagine that I was not very happy with this very textual focus of the age. And I think that has to do with all sorts of things, mainly because I just like images, but also because I think we are missing a very vital part of modern life, namely the visual part of modern life, right? So modern mass media includes more and more images, and that starts maybe with my illustrations in the 19th century, but of course it currently stands at the millions of pictures all of us upload to social media every day, right? So I think modern life has become, in fact, a little bit like it's almost saturated with images, and we need ways to include those in our analysis, I guess. So if we want to indeed study culture and modernity, we need to become lookers and not only being readers. That's also, I'm not sure if German is also included in one of the many official languages we are speaking here today, but as you can see on the slide, this two photographs from my favorite TV show of mine called Babylon Berlin, where the reporter is asked to supply pictures, and then the other guy says, like, we used to have readers, now we only have now we have lookers. So I think we need to become, in fact, lookers, or a little bit. So this is also reflected in the shape. This world of images is also reflected in the shape of digital collections. So these are, of course, from the KBR's own collection, and here you can see that there's, of course, lots of text, but there's, of course, also lots of images, which we can extract in all sorts of ways nowadays from the collections. So if we have a large collection of digitized newspapers or other digitized historical sources, we can in fact extract millions, maybe, or at least a couple of 100,000 images from these collections. So the question becomes then, what can we do with these images, right? And I think that here computer vision comes to the rescue, I guess. So computer vision allows us to analyze digitized images as data. So just as OCR, so optical character recognition, did for text, I think computer vision sort of provides us with a bottom-up access to images. And just as natural language processing did for DH, I think also other computer vision methods can be used to, in fact, find patterns in these large collections of images. So this also comes back to a sort of a methodological point in DH. So instead of looking at images one by one, which we can sort of describe as close reading, I think these computer vision techniques also allow us to look at many images at the same time, which you could describe as a form of distant reading. It has been called by my colleagues Lauren Tilton and Taylor Arnold. They call it distant viewing, and I think that's a very apt word for it. Right. So I imagine that many of you might not be familiar with how computer vision techniques actually work. And that's, of course, very understandable, as I gather most of you will be trained in the humanities. So I myself also trained in the humanities, so I hope that I explain these sort of things correctly. So if you are, in fact, a computer science and I say anything wrong, please don't hesitate to correct me later on. But as I see it, computer vision is basically a field in the computer sciences that tries to gain a high-level understanding of images using computational means. And this sort of high-level objective is divided in multiple tasks. And one of the most common tasks in the field of computer vision are image classification, object recognition, and scene detection. So there are other tasks, but I think these are the most prominent ones. So this sort of simply means that we basically want to have a computer draw boxes around things and then classify these things. And I think that many of you will be familiar with these sorts of images, which you can see here on the slide, right? These are from a collection which was used to train self-driving cars. But we can also think of, for example, facial recognition algorithms, which are used for surveillance. So I think we are indeed very familiar nowadays with these sorts of images. And I think they sort of look or might look deceptively simple, right? It might sound deceptively simple to have a computer draw boxes around objects on an image and then classify these things. But it's, in fact, it was until very recently a task which was almost considered to be unsolvable. So I think there are two sort of things from the 2010s onwards. Two things changed in that respect. So first of all, we had the introduction of new computer vision techniques, and most prominently a technique which is called convolutional neural networks, or CNNs. And the second thing is the sort of the increasing availability of large volumes of training data. So that's mainly data which was derived from the internet. So all the images of our cats, of our dogs and pets, which we uploaded to the internet, could also be leveraged by large companies such as Google in training these new visual artificial intelligence algorithm. But how does a ConvNet actually work, right? So I think for any understanding of how computational techniques can be used to study images, it's first very important to understand that for an image, a computer in fact does not see an image. For a computer, digital images simply consist of numbers. And you can see that here on the slide, right? So you can see that Abraham Lincoln, I hope some of you might have recognized him, here consists of all sorts of small dots on the screen, which are called pixels. And all these pixels have a number, a pixel value between 0 and 255, which denotes its visual intensity. So in the end, all these grids of numbers, so these pixel values, contain a sort of a visual signal that denotes visual things to us. So you can see here that the face of the US President Abraham Lincoln is sort of built up of these collection of numbers. So what a convolutional neural network basically does is it tries to reduce these grids of pixel values, so these digital images, into a form which is sort of easy to process. And it does so without losing the features, as they are often called, so the visual signals that are needed to predict the presence of a certain thing on that image. So in this case, we could, for example, think, what are the essential relationships between the pixel values that denote the visual face, or the visual face. It's of course always a visual face, but which denote the face of Abraham Lincoln to us. All right. So how does a convolutional neural network do this? And I think the term convolution is of course central here. So as you can see here happening on the slide, what a convolution basically is, it is a small square or kernel going over an image, and it changes the pixel value in the middle of the kernel based on the pixel values surrounding the kernel, surrounding it. And a convolution therefore basically strengthens or weakens certain signals which are on an image. And of course, many of you might be familiar with this sort of effect, for example, by the filters which you can find in Instagram and that sort of things. It's exactly the same process. So in the end, a convolutional neural network tries to sort of find the perfect settings of the dials, of a set of convolutions in order to identify the classes of the training set. So in the end, we try to find the perfect settings of all these convolutions in order to best find a certain visual signal. For example, again, harking back to the earlier example of Abraham Lincoln. Right. So I hope that it explains it a little bit, but how can these computer vision techniques help us to sort of unlock the visual side of digitized and digital collections? I think that the most importantly, or at the most basic level, all major tasks of computer vision, so image classification, object detection, and scene detection, can be used to automatically describe, so add metadata, in fact, to images. And this new metadata makes them discoverable for users that want to use the collections of heritage institutions, but also analyzable for researchers such as myself. And I think next to this sort of low-level stuff, this new metadata can also be used to describe entire collections, right? So we can use these new computer vision algorithms to identify dominant trends in a visual collection, but also important outliers, right? So images or groups of images that don't sort of conform to the general norm or general trend. And finally, and I think this is also very important as an historian, visual silences, as is often called in the archive, right? So sort of images which we don't have in the collection, or which are in fact sort of not present there. And this goes for both visual content, so what the images actually show, but also for questions of representation and also for questions of style. And I will now give you some examples of that sort of stuff, which basically come from my own research. So this is already a little bit of an older project, which I started when I was a research fellow at the Dutch National Library, so the KB. And I made this together with a programmer there called Willem-Jan Faber. And what we basically did is we extracted a large number, so 330,000 images from a sample of digitized Dutch newspapers, mostly for copyright concerns. So late 19th century and early 20th century digitized newspapers. And we trained an image classification algorithm to classify these images into all sorts of different categories. And in the end, we sort of decided that a couple of them were very relevant because they were very much like sort of, we were able to train algorithms on them, which is always a very good consideration to have, but also because these kinds of images were very prevalent in the collection. And there you could think, for example, of the chess problems and the weather reports. These are images that sort of appear over and over again in the collection, and they are also very similar, so that makes it quite easy to train an image classification algorithm on that. The same goes for another category, for example, the maps, which is also, they are in effect, if you look at the thousands of maps in these early 20th century newspapers, you see that they are in fact very similar in a visual way. But we also had classification, classification for algorithms for buildings, crowds, logos, schematics, so that's more of like building plans, that sort of stuff, sheet musics, and I think that's it. Yeah. So we can also use these image classification test to not classify what is actually on an image, but more what kind of an image it is. So as an historian of visual culture, I've always been very interested in what visual media are used to sort of represent the world. And I was very interested in a sort of this turnaround or turning point between the use of illustrations and photographs in Dutch newspapers. So with the help of my colleague Leo Impet, we trained an algorithm which was able to make a distinction between illustrations and photographs. And then here on the slide, you can see that, first of all, I think you can see on the figure, you can see that we see an enormous increase in the use of images from the 1920s onwards in Dutch newspapers. But you can also see that in 1926, I guess it is, photographs overtook illustrations as the sort of the primary visual medium for the first time. So I think that's a very sort of an interesting way of distant reading this turning point between different visual media. We can also use image classification in a more, in very interesting ways, in a very binary way. So this comes from research from my colleagues at the Alan Turing Institute in London. And what they basically started off with is a large collection of these ordnance survey maps, so digitized maps. They were very interested in the development of railway infrastructure in the UK. And what they did is basically train a model, a computer vision model that first divided these maps into all sorts of small squares. And then the model only had to say if an image contained railway infrastructure or not. And here you can see the results and what they in fact could use this new model to identify railway infrastructure in these maps, and therefore also sort of chart the development of railway infrastructure over time in the UK. And I think that's in general a very good idea to have these computer vision models are very good at binary tasks, so saying if something is A or B. So I think this is a very good application of them. Right. So what we also did at what I did at the KB is also we can combine all sorts of these different classifications in sort of interfaces that users of the archives can also use. So what you can see here is that we sort of connected our classified images, so the chronic images, to the text that accompanied the images. And then you can see that you have all sorts of new ways to look through the collection, for example, by selecting images that contain a face. So we recognize those with a facial algorithm. And then, for example, say president, you get a lot of images which in fact show presidents, mostly of the United States, or in this case also I think it's the Chinese president. Sun Yat-sen from the Chinese Republic. So this is a slightly newer application, but it's a little bit along similar lines of my colleague Ben Lee at the National Library of Congress, which is a wonderful project, which also allows you to look in all sorts of new ways through images that Ben extracted from the digitized American newspapers. So that's also highly recommended. So these basically until now, all the tasks which I talked about were image classification tasks. But now we can also see that we have, of course, object detection tasks. So which do not identify or classify an image on the image level, but in fact try to find specific objects on an image and then classifies what these objects are. And this example is from a very interesting, I think, research from new colleagues of mine at the University of Antwerp, which used an object or retrained an object detection model to identify stringed instruments in a large collection of paintings. Of course, you can imagine that you could apply this to all sorts of different, and it has been applied to for all sorts of different objects. For example, cars, planes. If you can think of an object, you can probably train an algorithm to recognize it in a large collection. So another task of computer vision has been facial recognition. Of course, it's a highly problematic task in all sorts of ways because it's often been misused for surveillance and that sort of stuff. But I think it's also a very interesting task if we want to study representation in large visual collections. So this is from research I did together with my colleague Melvin Wevers. And there we retrained a computer vision facial recognition system on historical material. In fact, on 1 million advertisements taken from the Dutch newspaper NRC between 1955 and 1995. And we used it to test a famous hypothesis by the sociologist Irving Goffman about the display of gender in advertisements. So Goffman sort of posited that men and women learn to, in fact, he was a little bit of a Judith Butler, pre-Judith Butler, but in fact learn to perform their gender from looking at advertisements. And he had all sorts of rules on how men and women were sort of interrelated on advertisements, and we tried to test those hypotheses. And in the end, I think, which was already interesting, we could, for example, say that, as you can see here on the slide, on the figure, that, for example, in the NRC, like in the 1950s and in the 1960s, you often had more women in general than men on an advertisement. But then from the 1970s onwards, we see that men become much more prevalent on advertisements. So this sort of shows, it can also be connected to a change in the management of the newspaper. But I think, in fact, it shows, for example, Melvin and I sort of think that this can be related to the increase of financial advertisements that showcase financial products. Here, this is also a little bit related to my current work at the HOA project, which Julie already mentioned, where we are also very much interested in representation and all sorts of biases. So so I think it's it's both problematic, of course, in all sorts of ways, and I would also be happy to answer questions about that, to have a computer vision algorithm recognize a person's gender, and there's many considerations which we should make here. I think it can also be a very powerful tool to sort of come to grips with these patterns of historical representation of men and women, of racist representation, sexist representation. So all sorts of these different biases that can exist in historical collections. This was more of an experiment, but I think it's also interesting is that, of course, all these models which we have trained have a very, in the end, they have a sort of an archetypical idea of what they are looking for. So in our case, they had a very archetypical idea of men and women in 1950s and 1960s advertisements. And nowadays, you can also use another technique called a GAN, or Generative Adversarial Network, to use this archetypical idea to create images from scratch, basically. So what we did here is we had again sort of made these men and women based on our collection of advertisements. That sort of might be able to sort of point out what the computer vision algorithm actually picks up upon. So what it is actually looking for, right? So then this, of course, requires further close reading to see what the signal actually is. Right. So we have all these different tasks. So image classification, object detection, facial recognition, and all these, in fact, all these tasks result, for all these tasks, the computer vision algorithm has to make this certain ID, so this archetypical ID. And it's often called a feature or an embedding, right? So all these images are in the end represented to the model as an enormous large connection of numbers. And these numbers then sort of result in the fact that you can place an image or a document, but in our cases, images in a large vector space, so a multi-dimensional space. And you can use all sorts of techniques to calculate the distance between different documents in this vector space. And that's sort of, I think colleagues at the DH lab of Yale realized that you could also use this to then cluster visually similar images in a collection. And I think so Pixplot, the tool they developed, is a very good example of how you can apply this. So here you can see, I think, an example from the Norwegian collection. And you can see, in fact, that the computer vision algorithm sort of picked up that all these different men mostly and women are, in fact, they should are visually similar, and they belong together, or they are clustered together. Right. So I've talked a lot about about the images which you can extract from newspapers and then analyze in all sorts of different ways. But being a historian of visual culture, I quickly realized that all these images in their original historical source, of course, are connected to different kinds of texts, right? So I think we should see that all these different images are in fact part of multimodal objects. So objects that consist of both text, but also of image, or image of text, image and text, sorry. So this sort of points me to the theory of multimodality, right? So that in fact most representation in modernity consists of is in fact multimodal, so consists of multiple modalities at the same time. And the sort of the question I came up with in the end was like, how can we sort of approach this computationally? Because it's a very hard problem, in fact, which you can see here on the slide. That's the problem of meaning multiplication. Sorry. So in fact, an image, the same in different image text combination, the same image and or text does not always mean the same thing, right? And Bateman, in his book on words and images, described that as a word here represented as an apple and an image represented as a banana. The meaning is not simply apple plus banana, but it's in fact apple times banana. And what you then get is, of course, different the whole time, or it's in fact very hard to distinguish the contribution of the apple and the banana. So before I go into too much of apples and banana, let's try to see how we can in fact sort of disentangle this connection between images and text. So this comes from research which I did together with Ruben Ros. And of course, you can use computer vision and textual analysis methods next to each other if you have the same image that is repeated over and over again, right? So then you have the same banana, and then it's just combined with different types of apples. So we applied this to a large collection of iconic photographs, which we extracted from the internet. And then we applied, so we had this large collection of both the photographs, but also the text from the web pages where they were published. And then we applied a topic model, a form of topic modeling on the text. And then we sort of plotted changes in the prominence of different topics over time. So here you can see that the meaning of the same image, so in this case, we are looking at as you can see here on the left side of the slide, for me at least, so the famous napalm girl photograph, you can see how that same image is sort of reconfigured in different meanings over time by different sorts of texts. And you can see here that the topic model C7, it became prominent in 2016 all of a sudden, and then dropped very rapidly again. And here you can see that it's connected to a topic which mentions Facebook, Aftenposten, Hansen, Norwegian, right? So we were wondering, what does this topic mean? You can see here that it was in fact the chief editor of the Norwegian newspaper Aftenposten, which posted the napalm girl on his Facebook. And then the picture was taken down by Facebook, or censored, as he would surely describe it, because it shows a naked child. But of course, it's also very relevant image to commemorate the Vietnam War. So I think this sort of shows how different text can give lots of different meanings to an image, and they all sort of contribute to the digital circulation of images. However, most of the times we do not, of course, have this sort of one image that keeps on being reconfigured with different text, but we just have lots of different images, which also with lots of different text. And here I think the recent introduction of multimodal machine learning is very interesting, and especially the introduction of a model called CLIP in early 2021. So clip is it seems similar than to computer vision techniques, but it is very different, in fact. So it was trained on almost 400 million image-text combination, which were all derived from the internet again. But then the task of CLIP was not to predict to classify an image or to predict the presence of an object on the image, but rather the task of CLIP was that given an image, it must predict which text it was originally paired with in the dataset. So just as the convolutions are sort of settings of a dial, CLIP tries to find the perfect settings of the dial to best accomplish this. Should not be text, sorry, but task here on the slide. So, and what that is, it tries to extract embeddings from both the images and text to then best be able to predict which text was originally paired with which image in the dataset. And the authors of the paper that introduced CLIP sort of hypothesized that this allowed CLIP to learn visual concepts from language, so that it could connect specific words to specific images. This is very different from most computer vision models that are only trained on or optimized for a very specific task, for example, for finding faces or for finding a limited number of objects. CLIP, on the other hand, has a very high performance in the wild, as it is called. So it performs very well on tasks for which it was not trained. So it can extract embeddings for images and then predict if any textual prompt you can think of would be likely connected to them. Right. So this, I think, is a huge, could be a huge step forward for, or in fact, a new practical revolution for digital heritage collections and also for research, right? Because we can use CLIP and similar multimodal networks, which are surely now being developed, to sort of automatically describe or add metadata to digitized collection without, and this is very important, I guess, task-specific training. We don't have to annotate any data, and that's of course already a very time, because both of the things are very time-consuming, but also very expensive. That's already would be a huge benefit. So this is from very recent work together with Mike Kestemont, where we tried to use CLIP to predict outside and inside scenes in a large collection of late 19th century magic lantern slides. And in fact, we showed that CLIP was very good at this. So it was very competitive with a computer vision model, which we had retrained for specifically for the task. So this is sort of a way in which CLIP could be used to add very sort of more or less simple metadata to images. And I think this is way more exciting. CLIP can not only be used for these for a wide range of very more or less simple texts, but also for highly complex classification tasks. So as many of you from the humanities might know, of course, many visual concepts such as a family, for example, are not purely visual. So therefore, it's very hard to train a computer vision algorithm for that specific task. But because CLIP has been trained on image-text combination, it is way better at predicting the presence of these sorts of complicated concepts. So this is from yet unpublished work, but also now at the BIAS project, where we try to use CLIP to extract images of the family from a large collection of digitized Dutch children's books. And here you can in fact see that CLIP was not only very good at sort of picking up on very archetypical families, right, which you can see in the upper left corner of the slide. So father and mother sitting around the table, father reading the newspaper, that sort of stuff. But it, for example, also picked up on all these different animal families, which you can see in the lower left corner of the image, where you can see a father dog or a mother dog with her pups, and a bear with also, I don't know how you call baby bears, but small bears. Now, well, all sorts of that sort of stuff. But what was in fact more interesting to us was that we can also learn a lot from the sort of the small mistakes that CLIP make. So here you can see that these images in the lower right corner of the slide, you can see that we had a lot of images which don't really show a family, but they do show concepts, visual concepts, which are very important for visual representation of family. So you can see we picked up a lot of elder daughters taking care of their younger siblings, and we also picked up a lot of girls with their dolls. And of course, these sort of shows the same thing, namely females in a sort of a caring position, which is apparently very important for Clip's idea of what a family should look like. I thought maybe now to close off, it would be fun to show what Clip can actually do in practice. So I was going to, yeah, I hope the, yeah. I don't know. I hope can you see my my Google Colab here?
Yes.
Yeah, okay,
Yes.
Great. So I hope it still works. So this was in fact, so here Clip is trained on, because it's timed out. Oh shit, yeah. So maybe I will just try to rerun everything, and then yeah, I think I will just, yeah, I will try to rerun and sort of give you an idea of what it can do, but maybe that's for the questions. I hope it is done before the questions are done, but I think so. So yeah, thank you very much, and I will be happy to answer any questions that you might have. Thanks.
Thank you so much, Thomas. I always miss the real clapping, so I hope you can hear me. I already see some hands up, so that's great. Really nice introduction as well for those of us that are not familiar with the C and N's, and that was a really nice layman's introduction to explaining also some of the core concepts and contributions of computer vision and how that can connect to humanities and cultural heritage work. And of course, extremely interesting always to get updates about what you've been working on and how you're applying these techniques. I will first go, let's see, I already saw a hand, but now it's down. Oh, someone had their hand up. Who would like to ask the first question?
I see a question in the chat.
Thank you. Indeed. Delphina, would you like to ask that question or have us read it out loud?
Sure, I can ask it. Yeah, I work with computer vision as well and digital humanities collections, especially with paintings. So this talk was very, very interesting. Thank you very much. I was wondering if Clip was trained on natural images, ImageNet, all of that kind of stuff, and if so, if in your work you're using Clip directly, or you're training it before to do, cross depiction, and if you're not training it, how are you dealing with it if there is lower performance? Thank you.
Yeah, thank you very much. So that's a very interesting question. So one of the main problems with Clip is that the data set on which it was trained is entirely proprietary. So we don't actually know what is in the data set, and that's of course problematic for all sorts of reasons. So again, my colleague Leo Impet is now working. He just received funding for a large project, also mostly on art and paintings, which sort of tries to discover the bias of Clip in this respect. What we do know is that instead of many computer vision techniques which were trained on, I should say, on natural images, so on photographs mostly, Clip was basically trained on more of a wild set of images on the internet. So we are sure that it's more receptive to other media, so to illustrations, to paintings, to all sorts of other stuff. So in that sense, I think it encompasses a wider variety of different visual media and visual styles. And then to come to your last part of your question, so you don't have to, that's the main benefit, right, of Clip, is that you don't have to retrain the model itself. You basically use the model to extract embeddings from your own collection of images, and then you can connect any prompt. So you just type in, and I'm hoping to show that to you in just a moment, but you can type in any prompt, or that's one of the techniques in which you can use Clip. You can then type in any prompt, and then it tries to, it extracts the embedding from the prompt, and then uses a cosine similarity score to connect this prompt to a range of images. So that's how it sort of works. I hope that sort of answers your question. Thanks.
Thank you very much. If I can ask a follow-up question, the fact that it is proprietary, and of course how that changes our ability to do explainable models, right? How do you deal with this in your own work, as someone who works in the intersection of computer science and the humanities? Because that's something that I struggle with, and I would love to hear if you have any kind of motto or how you deal with this kind of issues that we're dealing with in general.
Sorry. I sort of got to unmute myself. Yeah. So thank you. So yeah, that's very hard. So I don't have a clear answer to this just yet, because I think also because Clip is relatively new, we still have to find out lots of things about it. So in this recent work I did together with Mike Kestemont about the Magic Lantern slides, I think there's lots of problems with how, in fact, Clip is used to sort of do sort of classical computer vision tasks, and also to then sort of see how it performs. So because Clip mostly works not with sort of direct predictions, but mostly with these cosine similarity scores, there's also sort of problems with, I think, problems or at least questions about how we use traditional metrics of computer vision to sort of test the performance of Clip. And I lost a little bit my train of thought here, but so how do I deal with this, that we don't know what the bias of these models is? So I think one of the main problems is for Clip now, if you apply it, is that it's very hard to inspect or sort of interpret the performance of the model. So and it's the most pressing issue, I guess, is that we don't know. It's very hard if Clip returns what percentage of all the images you are searching for it actually returns. So I think the false, and I always have to be careful what I say, false negatives are always a big problem here. Yeah, so I think it's just a long way we are just a long way of trying to figure out how these sort of things influence Clip, and also what its biases are.
Great. A follow-up question to that, I think, in regards to proprietary software. Giorgio, would you like to ask your question concerning costs?
Yes, sorry, because despite I didn't know I didn't know anything about Clip, and I had the impression that despite the name OpenAI, it's a proprietary software. So I was literally wondering about what the costs are to use it, and how do you manage it in just that. Thank you.
Thanks. So this is a very good point. So OpenAI sounds open, but it's definitely not open, of course, because it's connected to all sorts of evil tech giants in the end. But what it's basically, the business model is that the training set is proprietary. The model is freely available for everybody to use. So I use it with a Google Colab, which I was just going to show you. But it's basically it's free to use. So it's not also not an API or anything. You can just use it for whatever task. Of course, you need computing power for it. That's also why I use Colab, because you need a GPU to use it. Yeah, but so in that sense, it is free. And I would say that maybe there is a question of if something is free, then you are probably the product, right? So you always have to be careful what free actually means. But for researchers, I think the application is pretty much free.
Great, thank you. There's a question in the chat from Letizia. She would like to ask if there are any specific object detection methods used to separate images from the text in newspaper scans. So how do we extract images from newspapers?
Yeah, that's a very interesting problem, and I think so. This is really where the work of Ben Lee on the newspaper navigator set has been instrumental. So he really trained a model to extract images from digitized newspaper pages. So in some collections, such as the one of the KB, the images have been tagged by the annotator. So it's basically a problem of segmentation, and there they have been tagged in the scans or the OCR, the OCRing of the pages. So in some collection we do in fact have information about where the images are on the page just in the metadata, right? But for most of like just plainly scanned digitized pages, you would have to use a model and there to extract the images. And there, I think the model of Ben is really good to do that. It can be way better, but I think his models are really like a great place to start there.
Great, thank you for that. Also at KBR, again, a lot of the Delpher newspaper portal. I never kind of know what platform. That's the Koninklijke Bibliotheek in the Netherlands. And this is the Royal Library of Belgium, just to not confuse them in these acronyms. I also wanted to mention then a KBR project, which is working on newspapers. And I see Dieter and Alec, do you maybe have the Newspaper Eye app? If that's allowed to be tried out, as then there's some image segmentation that we're doing within that project as well. So if anyone is specifically interested in KBR's collections, to contact the research coordinator there and also the work we're doing there. There's another question from Ivona. If I'm correct, your microphone was not working, so I will read it out loud. Thank you very much for your presentation. I was wondering if you have experience with image in motion. I mean, how the videos can be treated with the clip, and having in mind that it's very complex data. Thank you for your answer.
Yeah, that's a very important question. So in the end, of course, video or moving images are just collections of shots, right, of stills. So in that sense, they have been applied. All the computer vision techniques have been applied, in fact, they mostly have been specifically developed to work on moving images, right? Think of self-driving cars, think of surveillance via facial recognition. So yes, these techniques are definitely available, but until now they have not been very much applied to digital heritage collections. So I know of a great project by Maria Eriksson at Umeå, and I hope I pronounced it correctly. It's a Swedish university where they try to use these computer vision algorithms to track circulation of specific fragments of moving image sort of heritage. Yeah, there's also the work of my colleagues Laura Dilton and Taylor Arnold, which is also they've worked, for example, on Friends, the sitcom. So you have those examples, but there's still a lot of work to be done there, I guess.
All right. Is anyone else? I hope I didn't miss anything in the chat now, but indeed, I apologize. I didn't see that Dilawar Ali was present as well, who's been working on the image segmentation there. And Dilawar, if you'd like to say anything or show the app, you're welcome to, just to follow up on that.
Hello. Maybe I can also share some thoughts on the same thing, because it's also quite related to the newspaper work that I am also doing. Maybe if you want, I can share some of the slides as well for my demo.
Sure, Dilawar, yes.
Yeah, sure. Then it's here. So that's basically a newspaper AI demo that's is basically developed on the KBR datasets, and I am Dilawarili, a PhD scholar at ID Lab Uganda under supervision of Professor Stephen Verstock. Ilak and Kenzo are also my colleagues that who help with this KBR demo. So it's again the same story that historical newspaper contain a lot of information that you already have everything, but I will just quickly show my workflow where we did about the layout segmentation, image clustering, this similarity analysis, NAR, and some image quality improvement parts. What was the purpose? Because the current Belgica press platform supports a page level hits only. Like if you search a specific person name, it only gives you the page level results. But we are currently working on article level search results so that you can search any specific keyword with respect to articles that can be used for any humanity research case. So this is our generic workflow that we proposed. This work is still under review for publication. Just we mentioned here that it's just a complete workflow where we had image of newspaper, then we applied some segmentation and then extracting the text, and then 3 techniques for image clustering, linking, and quality improvement. So that's all combined to a searchability tool. So that's the first work that we did was the document layout analysis, because I think for any specific task, the article segmentation is really important, and it's definitely very complex because of the versatile, very vast style of newspapers that varies from 1885 till 1950, and now it's totally changed because in past, like you already heard that the newspaper contain only the text, and then I think in 1920s afterwards these images starts appearing in this text. So that's why the layout is totally changed. And in initial stages of newspaper, these are only single column, double column, 3 columns, and it's only from left to right. And now it's every newspaper can have many articles that are spread over multiple columns as well. So we made a basic layout so that to detect where the pictures are and where the text is. And then we also detected the heading. So here in the layout, you can see every red block represent the heading, and then green is a text, and then below is illustration, and you can also see some yellow dots that are the force stop point that are usually detected based on the line detection using OpenCV technique, so that you can forcefully stop that this article stops over here. We also did some clustering. It's the same like Ben, we discussed with Ben as well in the start. There are definitely in machine learning, you can do it in 2 different ways, either supervised or in an unsupervised way. The unsupervised way is really helpful when you don't know about your data set, because you have a lot of images and you don't know that which class, which image belongs to which class or how many classes you have in your data set. So it's just normally used for initial annotation parts, and then you can at least get to know about your data. And then after this, you can label some of your images, because for supervised learning, the 2 things are really required, that you know what is in your data set, and you also should have some labels information. At the moment, some classes like you have seen here, the war and crowd are not performing really well. Their score are a bit low. It's because like we have a very vast imbalance in the data set, and we are currently trying to solve. But definitely we have some nice results. Like here, we have the person face, and that face is also a class of portrait. So we are basically not focusing on single class classification, but it's a multi-class classification technique that we approached in this research scenario. Like you have a scene, and then you have to determine that it's either it's a building scene, or it's a scene of a sport, or it's a scene of a war, or any other thing. And it's the same case in the drawing as well. Either it's a map or it's a face, like it's a drawing of a face or some advertisement. Similarly,
Sorry
with
to cut you off, Dilor. Would you mind showing us the app if it's allowed to be public, and to put that in the chat? And then I didn't mean to cut you off, but I want to get back to Thomas's talk. But I just wanted to give you a space to say what work has been there, and also that Data KBR as the project will be organizing some workshops to talk about what Dilawar has started detailing here. So if you could just show us the app and put the link in there, if that's all right.
Yeah, sure. So that's the next slide. I skipped for
demonstrator.
And
Apologies.
here it's just that's the demonstrator website. And normally here you can go for all pages, and from each page, like you can just select any of the page, and then you can see your article segmentation parts. And then if you click any of the titles, you can find most similar articles related to the same story, or there are some other informations, like if you go there and you want to see some similar pictures, so if you select one of the picture, then you can find some similar images there as well. Also the sports, I will put this link in the chat, and maybe it's
thank you.
Thank
you for sharing that, and sorry for putting you on the spot. Not preparing, but thought it would be a nice connection, specifically. And it also highlights again how computer vision techniques are used in all parts of this process. So not only when what Thomas was focusing on, of course, once we have the images in a nice data set, but already extracting them as well. So thank you, Dilawar. And then please take a look at that demonstrator. I see another question from Letizia for Thomas. And then I'm wondering as well, Thomas, if you're how things are going there with the program. So, maybe. But first the question.
Oh yeah, first question. Yeah. Sorry.
How much reach? Oh, go ahead. How much reach? How much retraining did it require to extend object detection to work on paintings instead of real natural images?
Right. So this is also it really depends. Like it don't require nowadays. It doesn't require any retraining at all. So I think like many out of the box object detection models nowadays. So for example, there's this model with the name YOLO V5 indeed. So it's not like a sort, because I know, like I was very excited by Dilawar's work. So I now have to be careful that I don't misspeak about any computer science problems. But so there's this model called YOLO V5, which is really easily applicable also to paintings. So, and it also works really well, but it really depends on what kinds of categories of objects you are trying to recognize, right? So in fact, like people often think that object detection models can detect every and all objects, but most of these models only have a very limited range of objects they detect. For example, there's a famous data set or called COCO, so common objects in context, and it recognizes only 93 different classes. You have the ImageNet dataset, which for its object detection tests only recognizes 600 classes, right? So in fact, it really depends on if you're interested in recognizing, for example, potted plants, a really interesting category, which is basically in every computer vision dataset from the early 2000s onwards, then you are in luck because it's very easy. But if you're trying to recognize, for example, a stringed instrument, then you would have to retrain. And it really depends on the task, how many images you would need, right? So yeah, that's always hard to say. Some can be there are some methods such as the TensorFlow for poets methods, where you only need you train on top of extracted features, and there you only have to have like 25 positive and negative images. But it really depends on what kind of thing you're looking for, and it can be quite complicated. Maybe I can just share my screen, because now in fact it worked, and I was really thank you, Dilawar, for your presentation, because it was really exciting work actually. So great to see what is happening at the KBR, because I didn't see that already. So I hope you can now all see my Google Colab here. Yeah, that's right. So this, as you can see, sorry. As you can see here, here I extracted embeddings with clip for around 38,000 illustrations and images, which we collected from Dutch children's books. And here you can see how it works. So what we basically have is we asked the model to connect images to a textual prompt. And now it returns the 10 most similar images to this prompt. So here, for example, I can now show you in effect the teacher, right? So you can see here that it's not always the best result. So here you can see people are looking at sort of signs, but these are all clearly teachers here, right? So I think that's very interesting. And maybe to come back to what one of the problems that Leolawar also mentioned, that there are some categories which are very hard for a normal computer vision algorithm to train upon. For example, war, which is, I think, one of those concepts which is not purely visual, but also in many ways multimodal. So this is also interesting because it shows that clip. So you can see some images of war effect. So first to show these ones, so you can see that it's really good at picking up these kinds of images. But also what is very interesting is that clip as a multimodal model, one of its main problems is, in fact, or a major problem is that if there's the word which you are looking for is also on the image. So in this sense, you said Tinus in de war, which in de war means is a Dutch word for confused, but it's of course also the same as war. If that's on the image, then that will immediately result in a very high cosine similarity score, or at least a relatively high score. So in this case, still comparably be low, but still it turns up in the most 10 most the 10 best results. So maybe you can basically give it any prompt you have. So if anybody, so what it also means, for example, for our current project, which looks into bias, I could also, I would rather not, but you could ask it to provide you with racist images, and it will also return very racist images from this collection. And I think that's one of the things where these models can in potential be very useful, because racist is a very complex visual concept. But it's of course very important, I think, to study racist representation. So yeah.
Great, thank you for showing that. It's really nice to see theoretically how easy it is to run the model in a collab with your data set. I think there's a really nice follow-up question here, also related to some of the images you showed from Matthias. Would you like to ask your question?
Sure, can you hear me?
Yes.
Thanks very much to all those have been presenting for doing so. My question is, what is to experience, or what bias one needs to keep in mind if one uses algorithms that are trained on modern material, but it uses it for historical material? And the same would apply to, I mean, you were showing detecting images in context to the text. So how much is the text depending on its language, or how much do you depend on the language of the text? Is it alphabetic? Is it Latin script? What about non-Latin script? Things like that. Thanks.
Yeah, thank you for that. So that's a very important question. So I think this is also, so I want to end normally I end my presentations with not like what can humanities people learn from computer science, but also what might computer science be able to learn from the humanities. I think in this case, like applying computer vision algorithms to historical material, we are quickly confronted with the fact that, of course, vision is not static, it's historically specific, it is multimodal, it's contextual, and these are all sort of aspects of vision that computer scientists, some of them do, but most of them don't, they don't have an eye for, right? So you're right that there's indeed this historical bias because we have these algorithms which are trained on modern material. For example, for CLIP, this would mean that you could imagine that there are some categories in text which no longer exist in a visual form in the present, right? So this is something I'm very interested in now. It's something which has to be figure out. So is CLIP, for example, will it be able to identify images of objects via prompts that are no longer present in a visual form on the internet? So which it would have no sort of opportunity to have seen in its training data set. So I think that's a very interesting question, which we simply don't have the answer for. What we can, of course, always do is that you can retrain computer vision models and possibly also CLIP to deal with this problem. But maybe as a final point, for example, in our research on gender, what I think is very important, or interesting at least, is that you can also use this sort of downside of computer vision algorithms as a benefit, actually. So we know that our gender recognition algorithm was trained on modern material, so on modern gender norms in that sense. So we could see that, for example, there were parts of the 1950s and 1960s when the model performed less well, so it was less able to recognize gender. So that shows us that there was a discrepancy between our current gender display norms and those of the 1950s and 1960s. So that's what I also mean by using these algorithms to identify outliers or groups of images that don't adhere to the general trend or norm.
All right, thanks a lot.
All right, thank you, Thomas. There's also in the chat, for those of you following, a project in Dutch about newspapers, krant, and photos. Take a look at that. And I see Dilawar, you've raised your hand. Have a question or comment?
I just have a question regarding the demo that you showed now. Thomas, thanks for the demo as well. It's just about the language that it's like you put the language always in English. So because newspapers are either in Dutch or French or German or whatever language, then is this model is capable of handling these, or either we need the translation before putting that?
Yeah, thank you. That's a very good question. So basically what the go-to solution now, so we don't know if there's any, because again, we don't know the percentage of image text combination on which CLIP was trained, which were not English. So we are sure that there are some non-English, because the authors explain it that way, that there are at least some other like prevalent internet languages in the training set. But what is a very common solution nowadays is just use one of these very good translators, which are available like Google Translate, whatever, to first just translate your query into English and then apply it, right? So that's the main go-to solution. Also because most of the queries are very simple, so they say like, "Hey teacher, a picture of a cat," right? So these are all sentences which you can perfectly translate into English nowadays using Google Translate or whatever method you prefer from any language or almost any language. So that would be the go-to solution.
Yeah, thank you so much.
Great. Are there any further questions or comments for Thomas? No? I had a question then, Thomas. So imagine well, let's just say a student in history, since that's also your background, and I don't have any knowledge of any digital tools, but I do want to create a set of digital images, and I want to run these models and do object detection. What should I do? How do I get started?
Yeah, that's also always a very good question. So I guess there's a lot of already stuff out there there is a lot of just like general introductions into these machine learning tools, like data camp and that sort of stuff, where you can sort of have low-level entries into like coding. And I'm definitely not a good coder at all. So I'm of the copy and paste kind of type, right? So and then try to figure out if it works in the end. So So I think that's the introduction, especially of collabs and Jupyter notebooks, right, where code is explained more or less. So parts, short snippets of codes are explained by the authors and what they do. Really enabled me to understand how this kind of sometimes quite complicated code works. So I think that is really the way into it. Just find Jupyter notebooks and collabs which sort of use the model. This can be done by simply by Googling, right? But then there's also some more for students. There's hopefully I contribute to a lesson for the programming historian, which is still under review, but which hopefully comes out pretty soon, which mainly was authored by my colleague Daniel van Strien in London, and that's, I think, is quite a good introduction if you're interested in that. And there's also a notebook of Lauren Tilton and Taylor Arnold, which you can find on their GitHub, and also a notebook from me and Melvin, which you can also find on Melvin's GitHub. These are all sorts of different introductions.
Excellent. Thank you, Thomas. All right. If there are not any further questions, then I will close our session and thank Thomas again. What an amazing first talk, and also really good intro into what we can do with image processing and with cultural heritage collections. Thank you so much. I've learned so much and it was really inspiring. I'm going to